Hey folks, my name is Nathan Johnston. Welcome to Lecture 40 of Introductory Linear Algebra. In today's class, we're going to start talking about something called diagonalization, which is basically the punchline of this course. It's why we've done everything up until now. What diagonalization is, roughly speaking, is it's a way of letting us treat most matrices as if they were diagonal, or at least almost diagonal. Okay, remember diagonal matrices are really nice because, for example, when you multiply them, you just multiply them entry-wise. Okay, matrix multiplication is the same as entry-wise multiplication if the matrix that you're working with is diagonal. Okay, well, if you're able to diagonalize a matrix, then you're able to do multiplication with it almost as easily. Okay, so let's see how this works. So first off, let's start talking about a little bit more precisely about what diagonalization is. Okay, and then we'll see why it can be useful. Okay, so we say that a square matrix A is diagonalizable if we can write it in this way. If we can write A equals PDP inverse, where P is just some invertible matrix and D is just some diagonal matrix. So if there exists any diagonal matrix and invertible matrix such that this happens, then we say that the matrix is diagonalizable. And furthermore, this is a diagonalization of A. Okay, and to sort of get an idea for why being able to write A in this form would be useful, let's consider the problem of computing a large power of A. So suppose that we wanted to compute A to the power of 500, for example. Okay, well, there are a few different ways that we could go about computing this. One way that we could compute A to the power of 500 is we could just use the definition. What does it mean to take the 500th power of it? Well, you just write down 500 copies of A next to each other and then do all those matrix multiplications. And in particular, that's going to be 499 matrix multiplications, which sucks, right? Matrix multiplication is the worst. It's this big, long, ugly formula. It takes a long time to do. I don't want to do it 499 times. Okay, but I mean, if A happened to be diagonal, if A were a diagonal matrix, what would happen is, well, okay, let's just give names to its diagonal entries, call them A11 down to ANN, okay, and all the off-diagonal entries are zeros. Then when you compute the 500th power of A, well, that's the same as just computing the 500th power of each of the diagonal entries, right? Because it's just the same as multiplying those diagonal entries by themselves 499 times. Okay, because again, entry-wise multiplication and matrix multiplication, those are the same thing if the matrix that you're working with is diagonal. Okay, so we really wish that we were in a situation like this, where the matrix was diagonal. Not realistic, doesn't always happen, but we can sort of split the difference. We can get really close to this diagonal situation, even for most matrices. For diagonalizable matrices, what would happen is, well, okay, I can write A equals PDP inverse because my matrix happens to be diagonalizable. And now I'm going to take the 500th power of that expression, which, okay, so far it looks like it's going to suck, but watch what happens. Okay, A to the power 500 is PDP inverse to the power 500. Okay, and I'm just going to write, 500 copies of PDP inverse. Okay, so that's what's going on there. But now notice something, right? I've got a P inverse here next to a P. Those are going to cancel out, right? Inverse times matrix is just the identity. Same thing happens here. P inverse times P, that goes away. That's just the identity matrix. And same thing happens in between every single D in the middle, okay? All of the P's and P inverses that are in the middle there go away and just cancel out to the identity matrices. So when you simplify that down, what you actually get is P times D to the power 500 times P inverse. And that's really nice because D to the power 500, well, D is diagonal. You can compute that entry-wise, just like we did up here. You just take the 500th power of each of those diagonal entries. Okay? And then after that, all you've got to do is you've got to do 2 matrix multiplications. And that's true no matter what the power is up here. You can compute the 5,000,000th power of a matrix just by doing stuff on a diagonal and then 2 matrix multiplications. Okay, and that's a heck of a lot easier than just doing all of the matrix multiplications, right? Rather than just doing it by the definition, you can always do it this way via just 2 matrix multiplications. Okay, and that's the magic of diagonalization, or at least that's one of the pieces of magic of diagonalization. Okay, so great. Hopefully we believe that diagonalization could conceivably be useful. How do we actually do it though? How do we determine whether or not a matrix is diagonalizable? And if it is diagonalizable, how do we actually find that diagonalization? All right, so we're going to start off with a big beast of a theorem that answers both of these questions. All right, so the first part of the theorem tells us when a matrix is diagonalizable. It says that a matrix is diagonalizable if and only if that matrix has sort of a complete set of linearly independent eigenvectors, okay? So it's an n by n matrix. What we're going to do is we're going to sort of make as large as possible of a linearly independent set of eigenvectors, okay? So sort of collect as many eigenvectors together into a set as you can while keeping it linearly independent, okay? If you're able to make that set have n eigenvectors, then your matrix is diagonalizable. And actually that's if and only if. Okay, if you're not able to do that, like if every linearly independent set of eigenvectors has fewer than n members, it's not diagonalizable. Okay, so it's if and only if. Okay, furthermore, eigenvalues and eigenvectors tell us how to do the diagonalization as well. Okay, so this next part, this furthermore step, tells us how to do the diagonalization. It says, hey, if you've got some diagonalization, A equals PDP inverse, okay, well, the way you can construct P is you throw those n linearly independent eigenvectors into the matrix P as columns, right? And that gives you an n by n matrix, okay? Each column is an eigenvector, okay? And then the way you construct D is you just throw the corresponding eigenvalues down the diagonal of D, okay? And the only thing that you have to be careful of when you do this is that you place them in the same order, okay? So remember, every eigenvector corresponds to an eigenvalue and vice versa. Well, the first column of P should correspond to the first diagonal entry in D. The second column of P, that's, some eigenvector, that should correspond to the eigenvalue in the second entry of D, like the 2, 2 entry of D, and so on. Okay, so you're free to place these in any order you like you can throw the eigenvalues down the diagonal of D in any order you like, but you've got to be careful then that when you construct P, you put its eigenvectors as columns in the corresponding order, okay? They've got to match up. Alrighty, that's our big beast of a theorem, so let's try to prove it now, okay? And to sort of simplify things a little bit, what we're going to do is we're going to transform this desired equation, A equals PDP inverse. We're going to multiply both sides of that equation on the right by the matrix P. And when we do that, we're going to get the equivalent equation, AP equals PD, okay, right? The P inverse is going to cancel on the right, and we get a P on the left here. Okay, and these two equations, they're equivalent to each other as long as P is invertible, okay? If P is not invertible, then unfortunately there's no way to go back from this equation to the previous one, okay? So we're assuming all throughout all of this that we're working with this equation, but also P is invertible, okay? So how can we reason about whether or not we can find a P and a D that make this true? Well, what I'm going to do is I'm going to write P in terms of its columns and do block matrix multiplication. Okay, so I'm going to give a name to each of its columns. Okay, so I'm going to say P, well, its first column is P1, second column is P2, all the way up to its nth column, its last column is Pn. And then I do block matrix multiplication. And these are some tricks that we haven't seen recently, but we did see these tricks. We did them way back at the end of week 3. Okay, so if you have a block matrix that's represented in terms of its columns, if you multiply it on the left by any matrix, what happens is that matrix just goes in and multiplies each of its columns, right? Think of this as like you've got a 1 by 1 times a 1 by n. Okay, so that's the left-hand side up here, AP. Okay, and the right-hand side, I'd like to get PD also in terms of its columns. And this is only possible because D happens to be diagonal. Because D happens to be diagonal, what happens is P times D equals this over here. Each of the diagonal entries just multiplies the corresponding column of P, okay? So you just get D11 times P1, D22 times P2, all the way up to DNN times PN, okay? And that relies crucially on D being diagonal, okay? It's nothing like this is true for general matrices. All right, but now this is nice because we see that, hey, this equation that we want to be true, that's true if and only if these two matrices are equal to each other. In other words, if and only if all of their columns are the same as each other, right? So AP1 has got to equal D11P1. AP2 has got to equal D22P2, and so on, okay? So that's all that we've got written down here, okay? So again, now what we've got so far is this matrix is diagonalizable if and only if this happens for all P's and for all D's, okay? Like, for each J between 1 and n, this is true, okay? Okay, Well, this is just another way of saying that, these PJs, those are eigenvectors with corresponding eigenvalue djj, right? Remember, this is exactly the defining equation for eigenvalues and eigenvectors. All right, cool. So that's the connection. That's where the eigenvalue-eigenvector connection comes from. Okay, so all that's left, like we've proved about 95% of the theorem now, all that's left is to remind ourselves that, oh yeah, we also need P to be invertible. Where does that come from? Well, that comes from that you're not, like, we can't just choose these columns P1, P2 up to Pn arbitrarily, okay? If we want that matrix to be invertible, remember one of our theorems said that a matrix is invertible if and only if its columns form a linearly independent set. Okay, well, we just saw that, hey, its columns are necessarily eigenvectors, so it's diagonalizable, the matrix A is diagonalizable, if and only if those columns, the eigenvectors, form a linearly independent set. And we have to be able to find enough of them, a full set n of them, to fill out those columns. All right? So that's basically the proof. I mean, it's sort of a Cliff's Notes jumbled around version of the proof, but that's the idea there, okay? So to diagonalize something, eigenvalues on the diagonal, eigenvectors, corresponding eigenvectors in the same order as columns in P. All right, so let's illustrate this method. Let's diagonalize some matrix. And we've seen this matrix before, okay? This matrix 1, 2, 5, 4. Last week, we found the eigenvalues and eigenvectors of this matrix, which that's great. That gets us 95% of the way to a diagonalization, okay? So I'm just going to remind you, what are the eigenvalues and eigenvectors that we computed last week for this matrix? Well, one of the eigenvalues was -1 with corresponding eigenvector -1, 1. Okay, and actually, maybe I should remind you at this point, eigenvectors are very not unique. Like -1, 1 is one of the eigenvectors, -2, 2 is another one. You can pick whatever one you want, okay? It does not matter. Same thing happens over here, okay? Another one of the eigenvalues was 6 with corresponding eigenvector 2, 5, okay? And again, you could choose some different multiple of that 2, 5 there. It does not matter, okay? So just pick some eigenvector for each of the eigenvalues. All right. Now, the point is, when we pick these two eigenvectors here, hey, that forms a linearly independent set. This -1, 1, and 2, 5, that's a linearly independent set. So great, the matrix is diagonalizable because I found a set of eigenvectors that's big enough. This matrix is 2 by 2. I need a set of 2 eigenvectors that's linearly independent, and I've got it. All right, so how do I actually construct my diagonalization? Well, my diagonal matrix just has the eigenvalues along its diagonal. So this is -1 and 6. And you can put those down the diagonal in whatever order you like. I could have done 6 then -1 if I wanted to. That'd be fine. But then the rest of my diagonalization would change. Okay, that's okay. Like, diagonalizations are not unique is the point. They're sort of unique or almost unique up to reordering. Okay. And now what's P going to be? Well, you just take the corresponding eigenvectors in the same order, throw them in as columns, okay? So our first eigenvalue was -1, corresponding eigenvector was -1, 1, so that becomes our first column. Next eigenvalue was 6, okay? So take the corresponding eigenvector, 2, 5, that becomes your second column, and that's the matrix P in the diagonalization. Last piece we need is P inverse, but that's okay. We know how to compute inverses, okay? So we've got this matrix P here. Just invert it using your favorite method. You can use the Gauss-Jordan row elimination method, or you can use, I mean, this is a 2 by 2 matrix. You can just use the explicit formula for the inverse of a 2 by 2 matrix, and you get this guy over here. It's 1/7 times that junk. Okay, and if you want to do a sanity check here, if you want to really double check that this is a diagonalization, just multiply these guys out. Compute P times D times P inverse, and you'll see that you really do get A back again. Okay, so this really is a diagonalization. All right, well, what can we do with this diagonalization? Okay, well, like we said earlier, one of the nice things you can do with diagonalizations is you can compute large powers very, very quickly. Okay, so we're gonna do that, and actually we're not gonna compute a particular large power, but rather we're gonna come up with an explicit formula for any power of this matrix. All right, so that's gonna be our next example. Let's compute a formula for a to the power n, where a is just that same matrix that we just worked with up above. All right, our starting point here is just, well, remind ourselves of what the diagonalization is, because that's our lead in here, right? We need this diagonalization to do this. Okay, but then once you have your diagonalization, we talked about this earlier, a to the power n, it's just going to be p times d to the power n times p inverse, because when you multiply that out, all of the p inverses and p's in the middle are going to cancel out with each other. All right, so let's just plug in what we know. Plug in the pieces of the diagonalization that we computed up above. So this was the matrix P that we computed. Here's the matrix D that we computed. And here's the matrix P inverse that we computed. So this is just P D to the power n, P inverse. Okay? And now we just multiply all this junk out, and we'll get a formula for A to the power n. All right, so first thing I'm going to do this in steps. I'm just going to pull that 1 over 7 way out in front, okay? Just because I like my scalars at the very front. Just a convention. And then here, this diagonal matrix, it's raised to a power. Well, to raise a diagonal matrix to a power, just put that power on each of the diagonal entries. In other words, in this case, it's the eigenvalues. Those are what you're raising to the power. Okay, and now all I've got left to do is 2 matrix multiplications. I've got one here on the right and one here on the left. Do those 2 matrix multiplications, and then you'll be done. Okay, so I'm going to start off with the multiplication on the right, but you can do them in either order, right? Matrix multiplication, it's associative, so you can group, you can sort of put parentheses wherever you like. Here I've sort of put them around these right 2 matrices and done that matrix multiplication and left the left one alone for now. All right, and after you do this right matrix multiplication, well, you're going to get minus 1 to the n times minus 5, so that's where this comes from, right? Notice the power increased because I've got an extra minus sign, so one more negative power. And similarly for all the other entries, negative 1 to the power n times 2, and then 6 to the power n is multiplying by 1 and 1 to give us these entries down here. All right, so that's one of the 2 matrix multiplications, and now I've just got one left. Okay, let's do this matrix multiplication now. And when I do, I mean, I get something a little bit bigger and uglier. Okay, but now I'm done. Okay, that is my formula for a to the power n. No matter what power of n I want to compute now, I just plug n into this formula here. And yeah, it's a little bit ugly. But hopefully you agree that if I wanted to compute something like a to the power of 1,000, plugging 1,000 in here is a heck of a lot easier than doing a whole boatload of matrix multiplications, right? All right, let's maybe do a little bit of a sanity check. Let's double check our work here. Make sure that this formula is at least plausible, right? In particular, I'm just going to see what happens if I plug n equals 1 into it. And I'd better get a back again, right? If I plug n equals 1 into this, I'd better get a to the power 1, which is just a. So let's just do a quick sanity check, make sure that we do. Well, if I plug a to the power 1 in here, well, I get a minus 1 here, I get a 6 here, so that gives me minus 5 plus 12. And similarly, in all these other entries here, I'm going to get 2 times minus 1 squared, which is just 1, so I get 2, and then plus 12. Okay, and similarly down here, I mean, I get 5 plus 35 minus 2 plus 30. Okay, I add up those things in the entries, and then the 1/7, you know, divides each of those guys really nicely. And I end up with the matrix 1, 2, 5, 4 after I simplify things down. And if you scroll back up, yeah, that's the matrix A that we started with, right? 1, 2, 5, 4. Oh yeah, that's the matrix A, 1, 2, 5, 4. Okay, so the formula, it at least seems reasonable. Okay, so it seems like we did our work properly. Okay. All right, let's do one more example of this, okay? Let's go to this matrix here. This matrix is 0, -1, 1, 0. And let's find a formula for a to the power n. In other words, let's find a formula for just arbitrary powers of this matrix. And for this matrix, I'm going to note that there's 2 different ways that we could go. Okay, so method 1 is going to be the method we were just talking about, diagonalization. Okay, and then I'll talk about, you know, there's another way that you could do it for this particular matrix though too. All right, but let's go through diagonalization first. How do you compute, you know, a to the power n via diagonalization? Well, start off, get a diagonalization. How do you get diagonalization? Oh, I need eigenvalues and eigenvectors. Fortunately, again, I did that last week, okay? We saw this exact matrix last week, and we computed that its eigenvalues and eigenvectors. This was the example where we had to go to complex numbers. One of its eigenvalues was plus I, and it had corresponding eigenvector I1. And then another one of its eigenvalues was negative I, and it had negative I1 as one of its eigenvectors, okay? And if you construct this, you know, throw those 2 vectors into a set, you'll find that they're linearly independent, okay? So great. You know, that's a set of 2 linearly independent eigenvectors. It's a 2 by 2 matrix. My theorem from earlier in this video says, yeah, that matrix is diagonalizable. Great. And the way that you compute that diagonalization is you throw the eigenvalues down the diagonal of a diagonal matrix in whatever order you like. I'm just going to do I, then minus I. Okay, and then construct P by sticking the eigenvectors as columns into a matrix in the same order. Okay, so we started off with I, take the eigenvector corresponding to I as your first column. Then my next diagonal entry was minus I, take the corresponding eigenvector as your next column. Okay, great, so I know D, I know P. I also need P inverse, And I mean, we maybe haven't done this calculation with complex numbers before, but the exact same formula that works for 2 by 2 real matrices works for 2 by 2 complex matrices as well, okay? So you do 1 divided by AD minus BC out in front, and then you jumble up the entries inside the matrix, and you'll get exactly this. Or even the method based on Gaussian elimination, that also works for complex matrices, okay? It's not specific to real. So you can compute this inverse here using the exact same methods that we saw earlier in the course. Great, I've got a diagonalization now. Okay, so the way I compute a to the power n is I compute p d to the power n times p inverse, right? Because again, when you multiply out p d p inverse a whole bunch of times, all the interior p inverse p's cancel out. Okay, so you just need to take the nth power of the diagonal piece. All right, so just throw in the pieces of the diagonalization that we just computed. Okay, p goes here. D to the power n, well, that's all that's going on here. I've just raised each of the diagonal entries to the power n because that's how powers of diagonal matrices work. And then over here on the right, this is P inverse, and I've just taken this 1/2 and I've brought it all the way out in front because again, like scalars, like they commute with everything, so you can pull them out front. Okay, and now just do the matrix multiplication. Okay, so again, I like to do this rightmost matrix multiplication first, but you can do it in whatever order you like. If I do that rightmost matrix multiplication, I'm going to get this matrix here, and this left matrix just carried along for the ride. Okay, this 1/2 I minus I 1, 1 just carried along. I haven't done anything with it yet. Okay, but now I'm going to do this matrix multiplication, and what I'm going to get is I'm going to get this big, long, ugly expression. But again, even though this formula is kind of ugly, you probably agree that computing this by plugging in some particular value of n is a whole heck of a lot easier than actually multiplying a by itself over and over and over and over and over and over again, especially when n is large. Okay, so for example, I mean, like, let's make use of this formula for some particular value of n. Let's compute some power of a via this formula. And one thing that I'm going to note is, I mean, something might feel a little bit weird here. Okay, this matrix that we started with, it was real, right? I mean, all of its entries are real. Okay, but this formula that we just got for powers of it has complex numbers in it. So what the heck's going on here? Well, the really neat thing is, even though this formula has complex numbers in it, no matter what value of n you plug in, no matter what positive integer value of n you plug in, you're going to get a real matrix back out. Okay, all of the imaginary pieces are going to cancel out with each other, no matter what positive integer value of n you plug in. So for example, let's plug in n equals 3 into this formula and see what happens. Okay, well, if I plug in n equals 3, I'm literally just replacing all the n's by 3s. So this minus I to the n plus 2 becomes minus I to the 5. This minus 1 to the n plus 1 becomes minus 1 to the 4. And this I to the n plus 2 becomes I to the 5, and so on. Okay, just replacing all the n's by 3s to compute the third power of a via this formula. Okay, and now, well, let's look at what happens in each of these entries. Okay, powers of I, what happens is they just cycle around every fourth, right? Like I squared is minus 1, so I cubed is minus I, so I to the power 4 is just 1. Okay, and then after that, I to the power 5 is just going to be I again, okay? So every fourth power of I just repeats. They just jump between those four numbers. I minus 1, minus I 1, over and over and over and over again. So minus I to the power 5, that's just the same as minus I. Minus 1 to the power 4, that's 1. I to the power 5, that's just I. Okay, and do a similar calculation in the other entries. I to the power 4 is 1. Minus I to the power 4 is also 1. Okay, and similarly down here and down here. And notice exactly what I said was going to happen happens. The imaginary pieces all cancel out, and I'm just left with real numbers. Okay, after you simplify that down, you just get the matrix 0, 1, minus 1, 0. Okay, and I mean, if you go back to the original matrix A and actually compute A cubed by just multiplying it by itself twice, you'll get the exact same answer. Okay, so this sort of highlights one of the usefulnesses of complex numbers. Even if complex numbers feel really unintuitive to you, or like they feel like we're cheating, or we're introducing something that can't possibly help, because the original problem's in terms of real numbers. So what does a complex solution mean? Well, this is how complex numbers can be useful, even for real problems. Even though our solution is in terms of complex numbers, we can still get real answers out of it. Alrighty, so that's method 1 for computing powers of this particular matrix. There's another method that could work for this matrix though. And the thing to notice for this matrix is that, hey, this is actually a matrix that we've seen before, not just last week, but even way earlier in the course. Back in week 4, we saw this exact matrix because this matrix, it's a rotation matrix. Okay, this matrix, what it does is it takes two-dimensional space and just rotates it counterclockwise by pi over 2. Okay, this is one of those sort of standard matrices that we saw when we were looking at sort of geometrically motivated linear transformations. Okay, it's a counterclockwise rotation by pi over 2, and we saw that back in week 4. In other words, it's the matrix, we denoted it by r with a superscript pi over 2, and, it just takes every vector and rotates it like that, okay? And you can sort of see that from what it's doing to a vector v1, v2, it's turning it into minus v2, v1. It's sort of turning it into like the negative reciprocal of itself. Okay, so it's rotating it counterclockwise by pi over 2. So if we want to compute a power of this matrix, another way of going about it would be, well, you just take powers of rotations. And when you take powers of rotations, you just multiply the angle by whatever power you're taking. Right? So this rotation matrix to the power n, that's the same as the rotation matrix by an angle of n times pi over 2. Okay, just do a pi over 2 rotation n times. Okay, and we have formulas for rotation matrices, right? Remember, like our formula for this rotation matrix, it just has cosine of the angle in the top left corner and bottom right corner, has negative sine of that angle in the top right corner, and positive sine of that angle in the bottom left corner. Okay, so this formula here, this is another formula for a to the power n. It's actually the exact same formula as this one up here. It's just written in a different way. It looks really different on the surface, but it's the exact same formula. Okay, so if you're able to reason about your matrix geometrically, if you're able to interpret it as some linear transformation that acts geometrically in a fairly simple way, it might be easier to find powers of it sort of directly via that geometry. Okay, but the advantage of diagonalization is that it works in far more situations than that. For example, this matrix A that we worked through as our first example of coming up with a formula for powers of A. For this matrix, like, you're not going to have any hope of reasoning sort of directly geometrically. It's not just a rotation. It's not just a reflection. It's not just a projection. It's more complicated than that. So these situations are where diagonalization really shines. It lets us find patterns where those patterns aren't otherwise obvious. All right, that'll do it for today. Thanks for watching, everyone. Next class, we're going to introduce another theorem that's going to make it easier to show that certain matrices are diagonalizable. Okay, so I'll see you then for that.